Hello everyone, I am Dr. Sirajul Akfaisi. I welcome you in my YouTube channel. Today in this video, I am going to talk about optical isomerisms. So, what is optical isomerisms? Or what is optical activity? Optical isomerism is a type of stereoisomerism. You know, optical isomers have the ability to rotate the plane polarized light, and this property is often referred as optical activity. The beam of ordinary light consists of electromagnetic wave and that oscillate in an infinite number of planes at right angles to the direction of light travel. When a beam of ordinary light is passes through a device called a polarizer or a nickel prism made of calcite or calcium carbonate, light is found to vibrate in only one plane and is said to be plane polarized light. A light wave in all other plane are blocked out. Now you can see ordinary light and plane polarized light and see the differences. Now optical active compounds. When a beam of plane polarized light passes through a solution of certain organic molecules such as sugar or camphor, the plane polarized is rotated through an angle alpha. Not all organic substances exhibit this property, but those that do are said to be optical active. The angle of rotation can be measured with an instrument called a polarimeter. When a solution of known concentration of an optically active material is placed in a polarimeter, the beam of light is rotated either to the right clockwise or to the left anticlockwise. So the compound which rotates plane polarized light to the right clockwise is said to be dextrorotatory, and those which rotate the PPL light to left is said to be levorotatory. And dextrorotatory is indicated by positive sign and levorotatory is by a minus sign. So minus morphine, for example, is levorotatory and plus sucrose is dextrorotatory. You can see unpolarized light, light source, polarized light, polarizers, and simple tube containing organic molecules. You can see analyzer and then you can see the observer. So light source, unpolarized light, initial plane of polarized, polarizing filter, plane polarized light, solution of the chiral substance, plane polarized light after rotations of the plane polarizations, and angle of rotation of plane polarization. Here you can see the analyzer. Again you can see the light source, ordinary light, nickel prism, polarized light, simple solution, rotate polarized light by alpha. So, specific rotations. What is a specific rotation? The exchange of rotation depends on the number of optically active molecules encountered by the light beam. And this number in turn depends on the simple concentration and simple path length. If the concentration of sample is dot, the observed rotation doubles. If the concentration is kept constant but the length of the sample tube is double, the observed rotation doubles. In addition, the angles of rotation depends on the wavelength of the light used. To express optical rotation in a meaningful way, so the comparisons can be made, we have to choose a standard conditions. The specific rotation alpha d of a compound is defined as the observed rotation when light of 589.6 nanometer, 1 nanometer is equal to 10 to the minus 9 meter. Wavelength is used with the simple path length L of 1 decimeter, 1 decimeter is equal to 10 centimeter, and a simple concentration C of 1 gram per cubic centimeter. So you can see the observed rotation in degree, path length, decimeter, and concentration. So alpha divided by L into C. When optical rotation data is placed in this standard way, the specific rotation alpha d is a physical constant characteristic of a given optical active compound. For example, plus lactic acid has alpha d plus 3.82 and minus lactic acid has alpha d minus 3.82. So that is the two enantiomers rotate plane polarized light to the same extent but in opposite directions. Now you can see the penicillin V 233, 33, sucrose plus 66.47, camphor 44.26, chloroform 0, cholesterol minus 331.5, morphine minus 132, cocaine minus 16, and acetic acid 0. So 3 lactic acid are known: plus lactic acid, minus lactic acid, and plus minus lactic acid, racemic mixture. Since plus minus acid is only a mixture of plus and minus form, in reality lactic acid exists in two form, plus lactic acid and minus lactic, and these two acids are exactly identical in physical and chemical properties, but differ in their actions on the plane polarized light. So, such form of same compound which differ only in their optical properties are called optical isomers, and the phenomenon is termed optical isomerism. And optical active compounds exist in two isomeric forms that rotate the plane polarized light in opposite direction. The optical rotation power of two isomers are equal in magnitude but opposite in direction. So, what is plane of symmetry? A plane which divides an object to two equal halves is said to be plane of symmetry. For example, coffee cup has a plane of symmetry in comparison with the person's hand or shoes with lack a plane of symmetry. An object lacking a plane of symmetry is called chiral or disymmetric, while those having a plane of symmetry is referred to as a chiral. Now you can see here, you can see the symmetry. So symmetry plane you can see here, and not symmetry plane you can see here another molecule. So example, propanonic acid a chiral and lactic acid chiral. So figure you can see the mirror image relationship of the left and right hand. Notice that right hand is the mirror image of the left hand. So chiral carbon atom. A carbon atom which is bonded to four different carbon. It is also termed as handedness. Chiral carbon lacks the plane of symmetry and therefore called a dissymmetric or asymmetric. A chiral object cannot be superimposed on its mirror image. For example, a left hand does not possess a plane of symmetry and its mirror image is not another left hand but a right hand. The two are not identical and cannot be superimposed. If we lay one hand on the other, the fingers and thumbs would be clash. Now optical isomer. An optically active compound exists in two isomeric forms are rotate the plane polarized light in the opposite direction, and they are called optical isomers, and phenomenon is called optical isomerism. The optical rotation power of two isomers are equal in magnitude but opposite in directions. The equimolar mixture of two isomers will therefore not rotate the PPL at all is said to be racemic mixture. You know, optical isomers have the same physical properties, melting, boiling, and density. They have the same specific rotation but with the opposite sign. Now, optical activity of lactic acid. It contains one chiral carbon, lactic acid. The chiral carbon is shown by an asterisk. Three forms of lactic acid are known, of which two are optically active and third one is optically inactive. Lactic acid plus lactic acid minus lactic acid rotate PPL to the light clockwise and another way anti-clockwise, and does not rotate PPL is optically inactive because it is racemic mixture. Now you can see the molecules and melting point both same. Equimolar mixture of plus and minus forms racemic mixture. So isomers of lactic acid in the upper line to three-dimensional structure are shown. In the lower line, a commonly used Fisher projection is given. The vertical lines represent the bonds going away from the observer reader and horizontal line represent the bond coming toward the observer. Now conditions for optical isomers. Molecules should be disymmetric. Molecules should be dissymmetric. And this is the molecules should not be superimposable on its mirror image. Simply this dissymmetry results from the presence of a chiral carbon atom. Chiral carbon is the one which is bonded to four different groups. You can see. Now, non-superimposable mirror image forms of chiral carbon are called enantiomers, and they represent two optical isomers plus and minus. Their opposite rotationary powers are due to the opposite arrangement of the groups and around the chiral carbon. So, it is true that molecules containing chiral carbons are optically active, but it is not always so. There are some compounds such as mesotartaric acid which have chiral carbon, but is not optically active. On the other hand, there are some compounds which do not have chiral carbon but are optically active, substituted allenes and biphenyls. Now, optical isomers of tartaric acid. Tartaric acid contains two chiral carbon atoms. You can see four forms of tartaric acid are known, of which two are optically active and two are optically inactive. And the two optically active forms are mirror image of each carbonate, each atom, but not superimposable, that is, and are enantiomers. So, four form of tartaric acid positive, tartaric acid negative, rotate PPL light anticlockwise, another is clockwise. Mesotartaric acid is possesses a plane of symmetry and is optically inactive. This optically inactive form is said to be internal compensation, means optical rotation of one carbon atom is cancelled by the other. And plus minus tartaric does not rotate PPL and is optically inactive because it is a racemic mixture of plus and minus. So you can see here optically active, optically inactive, equimolar mixture of plus and minus. So term used to describe the optical isomer. A chiral molecules which cannot be superimposed on its mirror image. It is identical to its mirror image and do not rotate plane polarized line. Chiral center means what? For a molecules to have chiral, it must have at least one chiral center and carbon with four non-equivalent groups. Any molecule that contains a chiral center will be chiral unless the molecules has a plane of symmetry, in which case the molecule is a chiral mesoform. You know, the a chiral molecule is one that cannot be superimposed on its mirror image. It rotates the ppl. So what is diastromers? Diastromers are stereoisomers that are not mirror image of each other. For molecules to have a diastromers, it must contain more than one chiral center. What is enantiomers? Mirror image of each other are enantiomers. What is mesocompound? Compound that contain a chiral center but is achiral because of plane of symmetry. Optical active means what? Compound having the ability to rotate the ppl. Racemic mixture. What is racemic mixture? Racemic mixture is 50-50 mixture of two enantiomers. Racemic mixture do not rotate ppl. So what is the properties of enantiomers? You know, optical isomers that are mirror image are called enantiomers. These always exist as a discrete pairs. For example, there are two optical isomers of lactic acid. You can see A is the mirror image of B are the pair of enantiomers. Now, enantiomers are a stable, isolable compound that differ from one another in three-dimensional spatial arrangement. Enantiomers cannot be interconverted into the ordinary condition. Enantiomers have identical properties in all respects except in their interaction with the plane polarized light. And they have the same melting point, density, solubility, color, and reactivity towards acid and bases. And they differ, however, in the direction in which they rotate the ppl, but rotate the ppl to exactly the same extent, same angles, but one rotate the plane light to the right and to the left. So mixture of equal amount of the two enantiomer is racemic mixture. Such mixture is optically inactive because the two compound rotate ppl equally in opposite direction and cancel out one another. So what is the properties of diastromers? You know, the diastromers are in stereoisomers that are not mirror images of each other. For a molecules to have a diastromers, it must typically contains a chiral center. You know, in general, you know, in general, you can see here, uh, each chiral carbon atom in a molecule double the number of theoretically possible isomers. So, hence the molecules with the n number of chiral carbon atom have the 2n stereoisomers. So figure out the four isomers of 3-bromo-2-butanol which has two chiral carbon atom. Now notice that A is the mirror image of B, C is the mirror image of D. Thus the four isomers are two pairs of enantiomer. Now compare A with the C. They are neither superimposable nor they mirror image. They are called diastromers. You can see A and D are also diastromers as B and C and B and D. You can see. Diastromers have different properties. Two diastromers will have the different melting point, boiling point, and solubility. They will also have different reactivity toward the most reagent. Now, diastromers are stereoisomers that are not mirror image. Since we use the right hand, left hand analog to describe the relationship between two isomers, we might extend the analogy by the saying that the relationship between the isomers is like that of hand from different groups. Your hand and your friend's hand look similar, but they are not identical and they are not mirror image. So same is the true for diastromers, and they are similar, but they are not identical and they are not mirror image. So mesocompound. You know, the mesocompound is a compound molecule that contains a chiral center, but is a chiral as a result of having a plane of symmetry in the molecules. So a compound with two or more chiral carbon atom, but also having a plane of symmetry is called mesocompound. You know, the molecules having the plane of symmetry divide them midway between the two isomers chiral carbon in. You can see the meso 2,3 dihydroxybutane and mesotartaric acid. So notice that one half of the molecule is the mirror image of the other. Both molecules are optically inactive even though each has two chiral center. Neither will rotate the ppl. So you can see the meso 2,3 dihydroxybutane and mesotartaric acid. Now, friends, optical activity without asymmetric carbon. Compound containing a chiral carbon are optically active. However, there exists some compound which do not possess a chiral atom but are optically active, provided that the molecule is dissymmetric. You can see alene derivatives. Some derivative of alene exhibit optical isomerism. For example, 1,3-diphenyl propadiene. In alene, the central carbon atom forms sp2 sigma bond, and the central carbon has also two p orbitals which are mutually perpendicular, and these form pi bond with the p orbital on the other carbon atom. As a result, what happens? The substituents at one end of the molecules are in the plane, which is the perpendicular to the other substituent at the other end, so that the compound exists in the two forms which are non-superimposable mirror image and are optically active. Look at here, 1,3-diphenyl propentine. Now another example, biphenyl derivative. Substituted biphenyls show optical isomers when substituents in the two positions are large enough to prevent the rotation about the point joining, and two benzene ring. For example, biphenyl 2,2-disulfonic acid exists in two forms. You can see the biphenyl 2,2-sulfonic acid, a biphenyl. So these two forms are non-superimposable mirror image, and they do not interconvert at room temperature because the energy required to twist one ring through the 180 angles relative to the other is too high. And this is the turn because during the twisting process, the two SO3H groups must come into very close proximity when the two benzene rings become coplanar and strong repulsive forces are introduced. You can see. Now, resolution of racemic mixture. How you will resolve it? The synthesis of an optically active compound produces a mixture of plus and minus isomers in equal amount. Recall that these isomers are non-superimposable mirror image and are called enantiomers, and such mixture is called a racemic mixture of a racemate. The separation of racemic mixture into two optically active compound plus and minus is known as resolution. If the enantiomers are separated, the mixture is said to have the resolve. So mechanical separation, this method is developed by the Paschen in 1848. It is applicable to only solid substance which form well-defined crystal. Since crystal of the two forms differ in their shape, and this can be separated mechanically with the help of magnifying glass and tweezers. And this method is too tedious for the practical purpose and is now historically in test only because it was first method which Pasteur employed for the separation of tartaric acid. You can say these are two different. Now chemical resolutions, and this method is developed by Pasteur in 1858. It involved the use of optically active compound which could react easily selectively with either of the two enantiomers to produce a mixture of two diastereomers compound. You know, the compounds so formed have different physical properties and therefore can be separated by conventional method of separation, crystallization. The crystals of the diastereomers so obtained can be broken down chemically to obtain the two enantiomers separately. The separation of racemate into their component enantiomers is a process called resolution. You know, since enantiomers have identical physical properties such as solubility and melting point, therefore resolution is extremely difficult. So diastereomers on the other hand have the different physical properties, and this fact is used to achieve the resolution of the racemate. And reactions of a racemate with the enantiomenically pure chiral reagent gives a mixture of diastereomers which can be separated. So, for example, a solution of racemic lactic acid can be treated with an optically active base such as alkaloids brucine, and the resulting product will consist of two salt plus acid and minus base minus acid minus base. So, oppose the two enantiomers form of the lactic acid as represented by the symbols. So, and suppose the two enantiomers form of the brucine are represented by the symbol. So, inspection of the configuration of the two salts show that they are not super enantiomers. Therefore, they have different solubility in water and can be separated by fractional distillation and fractional crystallization. And the isolated salts are then treated with the dilute sulfuric acid and when the optically active acid are regenerated. So now we have the biochemical resolution. This method is developed by Paschen in 1858. In this method, one of the enantiomers is described biochemically using a suitable microorganism such as yeast, mold, or bacteria. The microorganism utilizes the one of the enantiomer for its growth and leave the other in the solution. The enantiomer step in the solution can be isolated by fractional crystallization. You know, penicillium glaucum removes dextroform from the racemic mixture of the ammonium tartrate, leaving a levoammonium tartrate. So disadvantage of the biochemical resolution, half of the material is lost. So this method cannot be used if the mixture is toxic to the microorganism. So kinetic method, you know the fact that Enantiomers react with the optically active substance at different rates is used for separation of racemic mixture. The procedure takes advantage of different inhibition state of the enantiomers with the chiral reagent. One enantiomers may react more rapidly there by leaving excess of the other enantiomers behind. So, a disadvantage of resolution of this type is that the more reactive enantiomers usually is not recoverable from the reaction mixture. So, my friend, selective adsorption and chiral chromatography, and that is the important. The sum time resolution may be achieved by passing a solution of the racemic over a column of the finely powdered optically active solution such as starch, sugar, or quartz, and the surface of the absorbent absorb selectively one enantiomers, and thus the solution emerging at the bottom is richer in the other enantiomer. So chromographic method whereby the stationary phase is a chiral reagent that absorb one enantiomers more strongly than the other have been used to dissolve the racemic mixture. Now, important resolutions. You know, the majority of the drug have many chiral center. For example, vitamin E has a 3 chiral center. Therefore, 8 forms are possible. Among these 8 forms, only one occurs naturally and 100% potent. Other 7 forms have different potencies, less than naturally occurring form. All form of vitamin E has a positive impact, but there are some cases where the other forms have a negative impact on the body, are harmful. One enantiomer is biologically active, and while the other is either inactive or very harmful. So the thalidomide story. The thalidomide was launched in October 1957 as an antiemetic drug that had an inhibitory effect on the morning sickness. That's why given to pregnant women to relieve morning sickness. It was later realized that while the positive form of the molecules was a safe and effective antiemetic, and form was an inactive tetragen, the drug caused numerous birth abnormalities when they're taken in the early stage of pregnancy because it contains a mixture of two forms. Majority of the born kids were having no legs, arm, finger, and this happened because the pharmaceutical company was unable to resolve the thalidomide. So, single enantiomers versus racemic mixture. A single enantiomers have less complex and more selective pharmacodynamic profile as compared to the racemic mixture, so have lesser adverse drug reactions, improve the therapeutic profile, less chances of drug interaction than the racemic mixture. Single enantiomers seem to be more advantageous over the racemic mixture as adverse drug reactions occur due to one enantiomers are avoided, but patients have exposed to less amount of drug, so body is exposed. So lesser molecule renals and haptic load of drug. There is a easier to therapeutic drug morning of the active pure active enantiomers. So racemization, the conversion of an optically active compound to serum into a racemic mixture is known as racemization. Racemization can be accompanied by the means of heat, light, or in conversion of the optically active isomers into optically inactive intermediate, which then revert to the racemic mixture. So the conversion of either of the optically active lactic acid into a racemic mixture by heating it aqueous solution may be proceed through an enol intermediate. You can see the plus enol form and acid and racemic mixture. So since the enol is the planar molecule, so the possibility of frontal and rarer attachment of hydrogen atom to carbon atom in the enol form is equal probability. Consequently, equal number of molecules of positive and form would result the racemic mixture would be produced, and three changes are inverted in actual practice. We get the equilibrium mixture. So the equilibrium mixture used and thus obtained contains one molecules and acid one another. So racemic mixture of the acid. So according to Pasteur, if a solution of plus tartaric acid is heated for some times at 165 degrees Celsius, it loses its optical activity, forming the racemic mixture and the meso acid. And this is due to the fact that tartaric acid having the two asymmetric carbon atom may undergo inversion of hydrogen and hydroxy only about one carbon or both yielding meso or tartaric acid respectively. You can see here. So optical active substance which cannot enolize because they have no hydrogen atom at a carbon to carbonyl group do not in general racemize except under condition which bring other chemical changes as well. So racemization of optically active halides. You know, the racemization of optically active halides may take place either by SN1 or SN2 mechanism depending upon the experimental condition. In polar solvent, S-butyl chloride racemized by SN1 mechanism, dissolution of the compound produce planar carbonium ion which can be recombined with the anion and Cl yielding both S and R form of the compound. You can see. So Optically active halide also can be deimized by SN2 mechanism, and solution of active 2-chlorobutane in acetone containing dissolved lithium chloride becomes racemic, and displacement of chloride ion of the halide by chloride ion from lithium chloride invert the configuration at the carbon atom undergoes substitution. A second such substitution regenerates the original enantiomers. Eventually, this back and forth process produces equal number of RNAs formed and substrate is then racemic. You can see here. So my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel and thanks for watching.